Okay, so let's take a look at our last example of the entire course, okay? So pause the video, there's a lot of reading here. If you please go through and read this and maybe figure out, see if there's anything you can figure out right away. Or you can give this a try on your own if you want, but go ahead and read through this and parts A and B. Okay, so part A says we're going to use a 0.1 level of significance to test the claim that there's a home field advantage in Major League Baseball, right? And then we'll answer part B, if there is, could that deviation just be from natural sampling variability, or is there really true evidence that there is a home field advantage? So as we look through this, I noticed a couple things, and you probably did too, that there was 2,429 games played in the 2011 season. So N in this case is equal to 2,429, all right? The number of games won was, the number of times the home team won was 1,277, right, out of those total 2,429 games. Now, you can go ahead and take that and figure out what P hat is if you want to, but right here they tell you that that's your P hat right there. In other words, they calculate for you, and the home team won 52.57% of the time. So P hat is really 0.5257. And if you take 1,277 divided by 2,429, you get the same thing. So let's go ahead and test the claim that there is a home field advantage. Now, I'm going to go to the next, so I'm going to print a blank slide to do that. So let's start with A and B. Okay. The null is that there is not a home field advantage. In other words, basically what that's basically saying is that the home team would win 50% of the time, the away team would win 50% of the time. Okay? So in other words, there's really no advantage. It's just at random, whoever wins, wins, and approximately, or each team will win, home team or away team will win about 50% of the time. Now the alternative would be, if there is a home field advantage, the home team is going to win more than 50% of the time. So this is a right-tailed test. Alpha is equal to 0.10. In other words, we're going to reject a true null hypothesis by about 10% of the time. Okay. Now the requirements. This seems to be what takes a little bit of the time. Okay. So first of all, it is a simple random sample, and it doesn't say that, but basically you're using one whole season out of the 100+ years of seasons there's been in Major League Baseball. So just like saying I'm going to pick up a package of M&Ms and use that package compared to all the M&Ms, it's the same thing here. We're just going to go ahead and assume that you know, this season represents the population of all seasons of baseball, and it's a simple random sample. So we're going to assume a simple random sample here if you just choose one season out of the 100+ seasons there have been in baseball. And maybe they did choose that season at random, who knows? But we're going to assume this. Okay? Secondly, the sample size. Is it less than 10% of the population? Well, your sample size here, how many games there were in the season, we're going to take 10 times 2,429 games that were played that season, and that will equal 24,290 games. Now, in all of Major League Baseball history, there's been hundreds of thousands of games played. I don't know if there's been over a million, but this is less than 10%. About 24,000 games is less than 10% of all the games that have been played over the 100+ years of Major League Baseball. So our sample is less than 10% of the population. And then finally, you take your sample size. Remember, this is N times our hypothesized proportion, which would be 2,429 games times 0.5, our hypothesized proportion, the percentage of times the home team would win the game, and they would win on average about 1,215 times, 0.5, and that is larger than 10. And then, to be honest with you, N times 1 minus our hypothesized proportion be the same thing. Why? Because 1 minus 0.5 is 0.5. So in essence, it's 1214, 0.5 also, and that's greater than 10. So we can go ahead and perform this hypothesized test on a standard normal distribution. Okay. So I'm going to again I'm going to pull up another slide or just add another one. And then we're going to draw ourselves a picture if necessary. Again, you don't have to do this if you don't want to. But this being a one-tailed test on a z distribution, and we're assuming in the alternative hypothesis that the home team wins more than 50% of the time, so you're going to put your alpha here on the right test. Why? Because the alternative was greater than. So alpha is equal 0.10. Okay, it's not like the two-tailed test we had last time. So let's calculate our test statistic now. So again, this would be, by the way, this is part E. If you chose to do it, part F would be to calculate the test statistic. So our test statistic is our sample proportion minus our hypothesized proportion all over the square root of our hypothesized proportion times 1 minus our hypothesized proportion all over, and you take the square root of that. Now, if you do the calculations very carefully, you get about 2.533. So our percentage for our sample is about 2.533 standard errors away from the center of this distribution. So how do we use that then? Well, we kind of calculate now our p-value. So G, we calculate our p-value. And to do that, as we've done before, we've got to go to our static. So our stat app here. Normal distribution. Find a probability, keep the mean and standard deviation same as mean means center. It's a right-tail test because of our alternative hypothesis, and it was 2.533. So, ladies and gents, what we get is right here is 0.57. This is our p-value as a percent, but again, if you want to change it to a decimal, you just move the decimal 2 places to the left, 0.0057. So what that means is that's about 6 thousandths. So roughly about 6 out of every 1,000 samples will be more extreme than ours. Meaning ours is that's a pretty extreme value. Okay? To only have 6 out of every 1,000 be more extreme than ours are, it means ours is pretty extreme. So we compare that to alpha. And ladies and gentlemen, I think we can safely say that that is less than alpha. So our p-value is less than alpha. So now finally we are going to reject the null. And what that says is that our sample data was extreme enough to say that there seems to be that the home team is winning more than 50% of the time, and it's not due to chance fluctuations. So there is sufficient sample evidence to say the home team wins more than 50% of the time. At least in Major League Baseball. Okay? Again, this doesn't have to do with like the NFL, college football, or anything like that. Now, the reason I wanted to just go back, there was one last question that it asked. It says, for part B, could this variation from 50% be explained just from natural sampling variability, or is there evidence to actually suggest that there is a home field advantage in Major League Baseball? Well, according to our data, our difference of our sample from the actual population, or excuse me, the difference from our sample from other samples, that's pretty extreme. Remember, only 6 out of every 1,000 samples would be more extreme than ours. So this isn't just due to sampling. By the way, this is part A here. So this just wasn't due to sampling distribution, this just wasn't due to sampling variability. It was due to actually there does seem to be a home field advantage. So to answer part B here, and again, I'm putting this in green because this is part A and part B, not to mix it up with the steps that we do in our sampling distribution. According to our results, the variability is not due to sampling variability, but there is strong evidence, and I mean, like I said, let me write this. It's only 6 out of every 1,000 samples would be more extreme than what we came up with. That's pretty strong evidence, but there is strong evidence of a home field advantage at least in Major League Baseball. All right, ladies and gents. So if you have, again, this can be kind of tough. So if you have questions, please feel free to give me a call or look over these videos again or email me. But this is your last example, so really all you got is a set of practice problems to do, and then I think we're going to call it a year, okay? All right, if you need anything, let me know. Please stay safe, stay healthy.